Hey guys, Miss Michelson here. Today I'm filming a video going over the Common Assessment 2 for geometry. And let me straighten this up and we're going to start on question number 1. Now, a lot of these questions should look familiar based on our first common assessment that I took, but now this one is going to be through topics 1 through 4. So the last one we did was just 1 and 2. This one's all of what we talked about in geometry so far. So if we take a look at problem number 1, it says if NOP is 39 degrees, so from N to O to P, right here is 39. And we know that NOQ, the whole angle is 142 degrees. It's asking us to find the measure of POQ, which is this angle over here. We know that small plus small equals big. Small plus small should equal 142. So if we're given the total, and we want to find one of the missing smaller sides, all we have to do is subtract here. So 142 minus 39 is going to give us the answer of 103 degrees. Number 2 is asking us to find the value of x, and I've got two pairs of intersecting lines. They share a vertex, which means that these are vertical angles. So what we know about vertical angles is that they are congruent to each other or they are equal, which means if I take my two expressions and put an equal sign in between them, then I can solve this equation. So the first thing I want to do is get x by itself. Well, I actually have two x's, so I need to get them all to one side of my equation. I'm going to take the smaller one and move it to the right side. So I'm going to subtract 4x from both sides. My 4x's on the left side are going to cancel out. Well, I guess that's the right side. 6x minus 4x is going to be 2x minus 45 equals 5. We want to add 45 to both sides. 2x equals 50. And then last but not least, I ran out of space, but we're going to divide both sides by 2. My 2's are going to cancel each other out. X equals 25. And that's my answer. Now we're moving into topic 2, which is our parallel lines cut by transversals. So we want to name all the pairs of alternate interior angles, and I've highlighted my interior. I'm in between those two parallel lines. Alternate means that we're going to have to be on opposite sides of the transversal. They're kind of like diagonal from each other. So I've got two pairs of alternate interior angles here. If we start with angle number 4, the one opposite of the red line, across from it is angle 5. So angle 4 and angle 5, there's a pair. And then if we look at angle 3 is also in the blue, directly across from it, opposite the red line, angle 3 and angle 6 are going to be my alternate interior angles. We're asked in number 4 if G and H are parallel to each other, and we know that the measure of angle 2 is 67 degrees. We want to know the measure of angle 5 over here. So we got to figure out the relationship between 2 and 5. Well, one is in the inside and one is in the outside, or interior and exterior, and they're both on the left-hand side of our transversals here. So 5 and 2 are what we call corresponding angles. And we know from our theorems that corresponding angles are congruent to each other. So if angle number 2 is 67 degrees, angle number 5 is going to be 67 degrees as well. We want to answer number 5, which equation represents a line perpendicular to y equals 4x plus 12. Remember, perpendicular means that we have opposite reciprocal slopes. Opposite reciprocal. So if we take a look at this equation right here, the slope of this line is the number in front of x. So our slope of our line here is 4. But the opposite reciprocal tells me that I can turn it into a fraction, and I want to flip my fraction and reverse the sign. So I'm looking for equations over here that have a slope of negative 1/4. Well, this one here, B, has a slope of 1/4, so I'm going to cross it out. This one here, C, has a slope of negative 1/4, so that one's going to work out. But if we look at options A and D, they're not written in slope-intercept form. We want to get them to look like y equals mx plus b. So if I take equation D and I subtract x from both sides, I would get 4y equals 12 and x aren't like terms, so I'm just going to write them side by side. And then I'm going to divide everything that I see by 4. So this is going to turn into y equals, because my y gets to be by itself. Remember, there's an invisible 1 out in front of that x, so it might be helpful to write this as negative 1/4, hint, hint, x plus 3. And there we can see this one definitely has a slope of negative 1/4. So we can circle D. If we try to do the same thing for option A, we're not going to get a slope of negative 1/4. So we can cross out A as well. If we select all that apply, it is C and D. All right, we can flip over. And now we're going to get into topic number 3, which was our transformations. Now, we were working on our transformation project, the whale project, in all of topic 3, and we always had our notes packet to reference what happens when we apply our transformations. So you might want to get your notes packet out if you were studying these problems. But I know that a reflection across the y-axis is going to make my ordered pairs negative x comma y. So if I have a point here, A, that is 5 comma negative 3, well, my rule tells me that I just make my x coordinate negative and my y coordinate gets to stay the same. So my answer here is going to be negative 5, negative 3. There's a fly flying around. Go away. All right, so we did a reflection. Our next problem is a translation that takes us from RST to R prime S prime T prime. So we're starting from here and we're going over to this triangle. Now, a translation is just a motion like to the right or to the left and up and down, and we can count the spaces on our graph between these corresponding points. So I'm going to take a look at the letter S here, and I'm asking myself, how much do I have to go to get from here to here? So I'm going to count horizontally first. I go over 1, 2, 3, 4, 5, 6, 7. And then I'm going to count vertically. I go 1, 2, 3. And because I went down 3, I'm going to make that a minus 3. And the way we write our translations is we have a capital T, we have these two little arrows here, and then we have spaces for an x coordinate or an x value, and then a y value as well. So in the x direction, I went over 7, and then in the y direction, I went down 3. So my translation here is to the right 7 and down 3. Can highlight and color code those guys. All right, we've got a similar problem in number 8, except for, what does it say? Oh, we're given the translation over here, and we're not given the picture. This time we're just given these ordered pairs. So we got to know that this means that I went to the left 3 and up 5. But also know that this 3 affects an x value and this 5 affects a y value. And we won't care about our points y here. So my 6 comma 3. To go left 3 means I'm going to subtract 3 from 6. 6 minus 3 is 3. And then to go up 5 means I'm going to add 5. 3 plus 5 is 8. Y prime has the ordered pair 3 comma 8. And then our next two are going to be our rotations. If we are looking at quadrilateral QRST, we're talking about point Q here. So I'm going to highlight it, and I'm going to write out what its ordered pair is. This is over 1, up 3. And a rotation 90 degrees about the origin is going to follow the rule negative y comma x. So the first thing we got to do with our ordered pair is we got to switch them 3 and 1 trade places, and then we make our y coordinate negative. Our rotation q prime is going to be negative 3 comma 1. Number 10 is using the same picture, but now we're looking at point R. So I'm going to find my ordered pairs for R is over 3 down 3, 3 comma negative 3. And rotating 270 about the origin is y comma negative x. So similar to what we did up here, except for the y coordinate changes signs this time. So the first thing we got to do is switch their spots. We would have negative 3 comma 3, and then the x spot switches signs, so I'm going to turn that to be a negative 3. And this is going to be my answer for r prime. How many lines of symmetry does a regular octagon have? Well, if we have a regular octagon, that means that it has 8 sides. And the lines of symmetry in a regular shape match up with the number of sides that it has. So if it has 8 sides, it has 8 lines of symmetry. So a hexagon would have 6 sides, a polygon would have, a pentagon would have 5 lines of symmetry. So it's always going to match up with their sides. This question number 12 I kind of like, but it's more of a visual question, I think. It's asking me what uppercase capital letters have rotational symmetry. So that means that if I were to take a letter, let's think about letter O, and I'm going to put a point here so we can orient ourselves. Rotational symmetry means that I can turn it, and at some point it's going to look like the original letter. So if I turn my O upside down, now my point's down here at the bottom, it looks like the O that I drew to begin with, so I know it has rotational symmetry. Another example could be like an X. If I put my dot up here and I'm rotating about that point, if I rotate my X, if I flip it upside down, now it looks like my X again. Now, of course, my handwriting isn't perfect, but if we were thinking about like a font on a computer, then our lines would be exact here. So some other examples of some letters in my capital alphabet that would work. Think about our H. If we rotate it, now my H is upside down, but it looks like an H again. So I can add H to my list. Some other letters that would work are I, N, S, and Z. So my extensive list here are O, X, H, I, N, S, Z. And then our next question here, it tells me that triangle ABC is reflected across the x-axis. So maybe we had a triangle over here, we reflect it, and it turns over, it goes across that's my y-axis. Whoopsies. Ignore that. It was reflected across the x-axis, so it flips down here. And our problem is asking us, are the two triangles congruent? Justify your answer. Well, we know that a reflection is just going to change where the triangle is located. It's not going to change its shape or its size. So by definition, yes, they are congruent. I'm going to say because the size and shape are preserved. And the reason why it's preserved is because we performed a rigid mode. All right, we can flip over to our last page. Now we are getting into our triangles, topic 4, the last thing that we did. It tells us what is QRP. So from Q to R to P, we're trying to find this angle. If PQS is 27, so from P to Q to S is 27. Well, the first thing I noticed is that we have 2 little markings here telling me that those 2 angles are congruent. So if this one's 27, this one's 27. And what that also tells me is because I've got an isosceles triangle, and we've got this line here that cuts that angle in half, we know that this must be a right triangle. So in my right triangle, if I draw a bigger picture here, this one's 27, this is my question mark. I know that this is 90, so I can write that in as well. So if I want to find a missing value in my triangle, all I got to do is take the two values that I know. 27 plus 90 is 117. And if I take that and I subtract it from 180, we would get 63. Let me check. 63. I think that's right. So my missing angle here is going to be 63 degrees. Number 15, we've got the same picture. We know QSP this time is 90 degrees, so that means this side's 90 as well. We know P to Q is 20, and from P to S is 12. What we're trying to find is from Q to S. And this here problem is going to be a Pythagorean theorem problem. So whenever we have a right triangle and we want to find a missing side length, we can always use the formula a squared plus b squared equals c squared. And we need to know what A, B, and C represent. Well, directly across from my right angle box is always my hypotenuse, and the hypotenuse is always C. So I'm going to replace C with 20, and don't forget to square. The next thing that I want to do is find A and B, and it doesn't matter. The two other sides can be A or B. So in this case, I'm just going to plug in a 12 for A, and I'm going to leave B alone. So I'm solving for this letter here, B. So the first thing I want to do is simplify my exponents. 12 squared is 144. B squared, I don't know. And 20 squared is 400. Now I want to get B by itself, so I subtract 144 from both sides. When I do that, I get B squared equals 256. And then the last thing that I want to do is I got to get rid of this exponent of 2. The opposite of squaring a number is taking the square root. And the square root of 256, if we put that into a calculator, equals 16. So my length of QS is 16. Number 16, funny, is asking us which criteria can be used to prove our two triangles are congruent. So let's take a look at what we have. We've got a side and a side. We've got an angle and an angle. And we've got a second angle in both of those triangles. So we have two A's and we have one S. So therefore, it can be ASA or AAS. The only difference here is the location of the sides. Does the side touch both of my highlighted angles, or is it just touching one of the A's? So the pink and the orange, does it both touch the blue side? No, it doesn't. So it can't be ASA. It has to be AAS. In question number 17, we want to find the value of x. Well, we know that x is trapped in this expression over here, which represents length AB. And we know that this triangle is congruent to it because we've got the same angle measures and the same side lengths here. So if this side is 7, then that must mean x plus 4 equals 7. So if we set those two equal to each other, we subtract 4 from both sides. X equals 3. Our list of all the ways to prove a triangle is congruent. Side, 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 angle, side, angle, side, angle, 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 side, and hypotenuse leg, hypotenuse leg. Speaking about HL, if we look at our triangle down here, this one sets off a little red flag in my mind because I've got a right triangle, and HL only works for right triangles. So that's the first theorem I'm going to check. So I got to check to see, is the hypotenuse marked on both of my triangles? This would be my H. And my H, it's marked, which tells me my two hypotenuses are congruent to each other. So that one checks out. Now the other marking on my picture, we got to make sure that a leg is marked as well. So we've got two. This represents a leg, this represents a leg. So what theorem can be used to prove these two triangles congruent? Hypotenuse leg. And last but certainly not least, in our picture here, which side is congruent to BD? So if we look at BD, it's this side right over here. It's kind of in this triangle. And if we take a look at our picture, we have a second triangle. So the side length that matches up with BD, it's this like longer diagonal side, would be AC. BD is congruent to AC. And that's going to be our last problem. If you have any questions, let me know.